Okay, we have one more reaction that I want to show you in Module 18, and the reason I left this one separate is it is entirely different from every reaction you've seen so far, and most of the reactions that you would see in this entire course. So this discovery, like a lot, came up by accident. Um, we know that when we react an alkene with HBr, we expect to get a Markovnikov addition. Right? We've seen this reaction before where we're going to add the bromine to the more substituted carbon. But it turns out sometimes chemists carrying out this reaction found that they were getting an anti-Markovnikov product and they couldn't figure out why. Um, Part of the reason stemmed from the fact that they were using ether as a solvent. And ether, if it's left out for a long time, exposed to oxygen, can get oxidized and have traces of peroxides in it. Peroxides, again, are molecules that have OO single bonds. Um, we've seen before OO single bonds make molecules reactive. And to explain what's going on here, we have to think about an entirely different kind of mechanism than any of the mechanisms you've seen so far. Um, this is going to be a radical reaction, meaning electrons are going to move one at a time rather than in pairs. So far, you're used to seeing us use double-headed arrows like this one here, where I'm breaking a bond and both electrons are going to the same side. Um, we call this heterolytic bond cleavage. The bond is breaking. Um, Heterolytic means the two sides don't get equal numbers of electrons. So different numbers of electrons in each side. In this case, the bromine gets both electrons, the carbon gets none. Um, that's where the hetero comes from. So different results for the two atoms. Um, if, on the other hand, we break a bond and give one electron to each side, and I want you to note the subtle difference here is that these arrows don't have a double head. They only have a single head. This is known as homolytic bond cleavage. Where we've broken the bond and given one electron to each side. So each side gets the same. Now, each of these bromine atoms now has an unpaired electron. That makes them what we call free radicals. Free radicals with that unpaired electron are generally very reactive. They're going out looking for something to bond with so that they can share that electron with someone. Um, and, you know, free radicals, you might hear about them in your body as being potentially dangerous. Having an excess of free radicals in your body can cause lots of undesirable reactions. When you eat things with antioxidants essentially are molecules that will scour free radicals and essentially neutralize their reactivity um, so that they don't cause damage in your body. Um, so with free radical mechanisms, I'm not going to have you draw many of these. I'll give you one example to draw on the skill builder, but it's useful to be exposed to this kind of reaction mechanism. And we can use it to understand what's going on here. So generally, free radical reactions start with what we call an initiation step. An initiation step means you are creating your radicals. To get the reaction started. Um, so in this case, the initiation steps are you have your peroxide, and that OO single bond is relatively weak. So often just light or heat, depending on how warm the mixture is, can cause that homolytic cleavage to create two OR radicals. those OR radicals are reactive, and one of them can come along and form a bond to the hydrogen from HBr, right? So if I want to be more explicit about this, we're essentially taking these two electrons, one from here, one from the bond, and we're using them to form this new OH bond. And then the leftover electron from the bond becomes a radical on bromine. It's really this bromine radical that this is really starting the reaction with the alkene. So this is our important species for reacting with the alkene. So initiation is just the process where we create some of these bromine radicals in our mixture. So now once I have a bromine radical, it's going to react with the alkene. And there's a couple of different ways it could happen. All right. I want to consider a Markovnikov pathway and consider an anti-Markovnikov pathway, and then think about why one would be preferred, in this case, the anti-Markovnikov. So in the Markovnikov pathway, we'd be adding the bromine to the more substituted carbon. So the way I would represent that is I would have this bromine radical form a bond with the one of the electrons from the CC pi bond. The other electron from the CC pi bond is going to become a radical on the end of the chain. So that's going to give me a radical here. And now these two electrons have created a bond to bromine. And then my second step, and this is what we call propagation. During propagation, we're always going to regenerate our reactive radical. So this molecule can react with a molecule of HBr, where one electron from the HBr bond comes with the hydrogen and forms a bond to the radical. So that gives me my product. But note, it also is going to regenerate a bromine radical. So it regenerates. This is why it's called propagation, because this can just keep going on until we start to run low on HBr. So this propagation will keep going until we start to run low on HBr. So that would be the Markovnikov pathway. Excuse me. If I consider the anti-Markovnikov pathway, that would be adding the bromine to the less substituted carbon and putting the radical on the more substituted carbon. Oops. So now I would have my bromine bonded out here. I've created this pink bond. And then in my second propagation step, now HBr, the hydrogen is going to bond to carbon, and I'm going to regenerate my bromine radical. So I asked myself, which of these two pathways is going to be more favorable? Well, a radical is an electron deficient species, meaning it doesn't have a full octet. And I have my choice of having a secondary radical or a primary radical. Just like carbocations, more substituents will be stabilizing. So a secondary radical will be more stable than a primary radical, just like a secondary carbocation is more stable than a primary carbocation. So this follows the same trend as carbocations, which we've seen before. So what that tells me is this pathway is going to be slower, so we don't observe this product. This pathway is going to be faster, so this is the observed product. So we're when these peroxides are present, our preferred pathway will actually give us the anti-Markovnikov addition. If you're curious, radical reactions, I've shown you initiation, I've shown you propagation, but at some point, we start to run low on our reactants. So when we start to run low on our reactants, then our new radical that gets formed is likely to bump into another radical rather than another reactant. And that's when the reaction terminates. We get termination steps that will lead to byproducts. These will generally be small in concentration, but we will get some of these byproducts from the case where any two radicals meet up and form a bond. And that ends the reaction sequence. So HBr addition with peroxides can give us an alkyl halide at the less substituted carbon. That's the takeaway here. And that pretty much covers all the reactions that I want you to know of alkenes, at least for now. One thing I'll do in one separate final video is start to think about how we can bring order to what we know of all the reactions. And for every reaction you learn in organic chemistry, there are really four things you need to know, or four categories of things you need to know. You want to know what the starting material is. You want to know what reagents are used. You want to know what products are produced. And then you want to know some things about the mechanism, the stereochemistry, the regiochemistry. So this last column for mechanism notes, that is sort of a catch-all for other information you need to know about the reactions. I encourage people to make a 4-column table for this. Some people make flashcards to learn reactions. The issue with flashcards is they have two sides, and really there's four things you want to know. 4-column table is helpful because then you can cover up one column at a time and quiz yourself to make sure that you're learning those different pieces of information. So I did attach this to the notes for this module so that you could start filling it in. I'm not going to go ahead and fill it in right now, but I would encourage you to go back and look at the reaction on each page and start to fill in these four pieces of information. Just to get you started, why don't we do the one reaction that we just learned, and that was this free radical addition of HBr to alkenes. So if I look at that reaction, my starting material was an alkene. Now in your table, I would encourage you to definitely list everything by functional group. If you want to put in a specific example, you can. So I would say alkene is my starting material. I might draw a simple alkene there. The reagents we're using here were HBr and peroxides. You could write that as ROOR, or you could write that as peroxides. Now, how would I categorize this product? So this product that was made, again, I started with an alkene. I ended with, well, this is what we would call an alkyl halide. So I would fill in as my product alkyl halide. And then I would draw that specific product for the starting material that I drew. And then additionally, the things that I want to know about this, the mechanism, I would want to know that this goes through a radical mechanism. that it gives anti-Markovnikov addition. Another way to say that is Br to the less substituted carbon. So to start to organize your thinking about all the reactions you've seen, I'd encourage you to go through the notes for module 15, or module 16, 17, and 18, and fill in each of those reactions in this table. And that's my closing thought for module 18. Let me know what questions you have.